Okay, this is the last topic that we're going to cover as far as factoring goes. These are some fairly advanced factoring techniques. And we've got our complete list of factoring rules here. Always start by factoring out the GCF. That's going to make our job a little bit easier. Take out the leading sign. And then the last one, always factor completely and make sure that we include all the factors in the final answer. A lot of these advanced factoring techniques are going to take advantage of this idea right here. Sometimes we might not be able to see how it fits one of these patterns here, but we might be able to rearrange things so that it does fit one of those patterns. And that's what we're going to do on this first one. We're going to notice that with these trinomials, as far as the variables go, we typically run into things where we've got this exponent where it's squared and this exponent where it's raised to the first. But you'll notice that going this way, this one is always twice the size, twice the exponent the one in the middle is. So we're going to use that idea to our advantage on this first one. So let's go ahead and take a look at this. This is part 2, example 5. And we want to be able to apply those ideas above in order to factor these. So we're going to take a look at this one right here. And what we're going to notice is this is squared, which is unusual. Normally the squared term comes right here. But you'll notice that if I double that, I get this right here. So basically what this is going to be is this is going to be x squared minus 13 times x squared, and then plus 36. So this is the variable part of this, and we want to make an x to the fourth. So a couple different ways to think of this. One way we could do this is just to say, look, I'm going to try and factor this trinomial into a binomial like I normally do. So I'm going to write down a set of parentheses, and then I'm going to do an x squared here and an x squared here, knowing that that's probably the way we're going to make an x to the fourth. And notice that when I put a number here, it's going to get multiplied by the x squared. If I put a number here, it's going to get multiplied by the x squared. That's going to make the middle term where we combine those together. That's going to make that an x squared also. So let's ignore the fact that this is squared. And let's just take a look at this one's squared and that one's to the fourth power. And let's just take a look at the numbers. This leading coefficient is a 1, so it's an easy trinomial if we want to think of it that way. And then they multiply. We're looking for numbers that multiply to be positive 36 that combine to be negative 13. So multiply to be 36, combine to be negative 13. So 1 and 36, we couldn't make a 13 out of those. 2 and 18, we can't make a 13 out of those. 3 and 12, can't make a 13 out of those, but 4 and 9, you can make a 13 out of those. And if they're both negative, let's just take a double check. They multiply to be positive 36 and they combine to be negative 13. So I'm going to write x squared minus 4, and I'm going to write x squared minus 9. And then we always want to factor completely, so let's take a look at this. Now I've got a binomial here times a binomial there, and we've got some ways to factor binomials now. We've got difference of squares, difference of cubes, and sum of cubes. This happens to be a perfect square of x and a perfect square of 2, and it's a difference, so this is going to factor to x minus 2 and x plus 2. That's a perfect square of x. That's a perfect square of 3. So this one's going to factor to x minus 3 and x plus 3. So out of that trinomial right there, it actually breaks down into all 4 of these factors right here. Okay, so a bit of an advanced technique. You can see how we break it down once and then break it down again. On this next one, so this is on B, we've got this ugly fraction right here with a whole bunch of squared variables, minus 600. Looks really messy. It is a binomial, so again, we've only got difference of squares, difference of cubes, and sum of cubes. But the first thing we want to deal with is we want to get that fraction out of the way. And the best way to deal with fractions is get a common denominator. So I'm going to write denominator right here. And let's go ahead and get a common denominator. So I'm going to put a 1 down here. And if I get a common denominator, this is going to be a 2, and the top's going to be a 1200. So 1200 over 2 is the same as 600. Now let's start taking out common factors. Out of the denominator, you can take out a 2, so we'll go ahead and take out a 2. And out of the numerator, I can't take out any variables out of the 2 of them, but I can take out a 3. So we're going to take out 3 halves, basically. And if I take a 3 out of 1200, I end up with 400. So here's what I have. I've got the variables left, x squared, y squared, and z squared, minus, this is going to be a 400 when I take out a 3. And then I take a look at this. Again, this is still a binomial. Maybe it's factorable, maybe it's not. This is a difference. It might be a difference of squares or a difference of cubes. This is definitely not a cube, so this is a perfect square of x, y, and z. And 400, if you need a calculator, pull out a calculator, take the square root of that. It happens to be 20. So 400 is a perfect square of 20. So here's what we get. We get 3 halves, and then it's going to be the first one minus the second one. So x, y, z minus the second one. And then it's going to be the first one, which is x, y, z plus the second one. So plus 20 right there. And again, if I were to multiply these together, they would multiply to be that original binomial that we had right there. Okay? All right, I'll slide over and take a look at this next one. This one has 4 terms. So remember, when we factor 4 terms, we normally group them like this. Group the first 2 together and the last 2 together. Looks a little bit hopeful here because we've got a difference of squares, b squared minus c squared. We could probably factor that. But we've got b's and c's here, and we've got a's and b's here. So even if we were to take something out of this, even if we were to factor the b squared minus c squared, we're not going to have any common factors between the two of them. So we do something kind of clever. Let's take the 3 of those and put those together, and let's leave this one hanging off the end for just a second. And what we'll notice is this fits one of those patterns. That's a perfect square of A, that's a perfect square of B. When I multiply them together, I get AB, and if I double it, I get the right middle term. So these 3 terms, those first 3, that trinomial right there, is a perfect trinomial square. So this is A plus B quantity squared minus this thing hanging off on the end. And I suppose we could just try and leave it there, but remember, this is a factoring problem, so we've got to turn it into a multiplication problem, and right now we've got a subtraction problem. As ugly as this looks, this is still a binomial. It's this squared minus this squared. So it's 2 terms. It happens to be a difference, perfect square minus a perfect square, so it's going to factor into this. The first one, which is a plus b, minus the second one, which is c, and then the first one, which is a plus b, plus the second one, which is c. And that right there is the answer. All done. Let's slide over and take a look at this next row. These are going to be a little bit challenging here. So let's take a look at y to the 6th minus z to the 6th. So if we've got y to the 6th minus z to the 6th, we've actually got a couple of options here. One thing that we could do is we could recognize that if I raise something to the 6th, we could write that as a perfect cube. So I could write this as y squared cubed minus z squared cubed. Now, when we write it down that way, we're relying on the fact that we know rules for exponents really well. Remember, if you've got a power to a power, we can multiply these together, so that would be y to the 6th, and then same for the z. The other option would be to just flip-flop these. So we could write this as y to the 3rd squared minus, this is going to be a z here. So this is going to be z to the 3rd squared. So if we've got an option between doing difference of cubes and difference of squares, let's come back up here and let's take a look at which one might be a better option. So I've got the difference of squares formula right here. It factors into 2 binomials. And the difference of cubes formula right here, it factors into a binomial and then a trinomial. And then the interesting thing is this trinomial is not factorable. Okay, we're kind of stuck with that. Whereas if we do it as a difference of squares, it factors into binomial and a binomial, and we've got some tools for working with binomials, so we may get lucky. So let's go ahead and do the difference of squares first. So let's come down here. I'm going to ignore this one, and this is going to be, y cubed minus z cubed. So first one minus the second one, and then y cubed plus z cubed. And you'll notice that these are binomials, and they're perfect cubes minus a perfect cube plus a perfect cube. So this first one is a difference of cubes. The second one is a sum of cubes. So this is going to be the first one minus the second one. Then it's going to be the first one squared, the 2 of them multiplied together. And we've already used the minus here, so this has got to be a plus. So this is going to be a yz, and then plus the second one squared. And then, so we're done with this one, so we've kind of broken it down here. Now it's this one's turn, so this is going to be the first one plus the second one. And then remember, there's always one negative here, and it's always in the middle. So if it's not in the middle of the first one, it's got to be in the middle of the next one. So this is going to be first one squared minus the 2 of them multiplied together, and then plus the second one squared. And that right there is the answer. So that big, long, ugly mess, if we were to multiply all those together, which would take quite a while, it's actually harder to multiply those together than it is to factor it, we'd get right back to this one. Okay, and those negatives are important because they're what makes it so parts of those cancel out. So let's take a look at the next one here. On this one, we've got a negative 343q to the third. So the fact that this is to the third clues us in that this is probably going to be either a sum of cubes or a difference of cubes. We could actually treat this as a sum of cubes. So got a couple of options here. I could think of this as negative 7q, and this is a perfect cube of 2, and I could do it that way. I could also factor out a negative if I like that better, and we typically don't like the leading coefficient. The leading coefficient to be negative. So again, although this would work a couple different ways, I like doing it this way. So what I'm going to do is I'm going to factor out the negative, and we're going to have 343q to the third minus 8. Okay, so I've got the negative sitting out front. Let me put a little wall here so we don't interrupt that. This is a perfect cube of 7q. Make that look like a 7q. Perfect cube of 2. So we've got the negative out front, and then this is going to be a first one minus the second one. Then it's going to be the first one squared, so that's going to be 49q squared. The two of them multiplied together, so that's going to be a 14q. And remember, if we've already used the minus right here, we're going to put a minus in the middle of a plus in front of that one, because remember, we only have one negative in these formulas. And then it's going to end with that second one squared, so that's going to be a 4. All right, so we're going to circle all of this together. And again, that's not the only way to do it. But that does make it so all of the leading signs here are positive. So we've got a leading sign of 7q, leading sign here, positive 7q and positive 49q squared. All right, let's take a look at this next one. Before we do, as maybe kind of a challenge problem, you might want to think about what would happen if we did do this as 7q. So that's a perfect cube of 7q. And then this is, we're going to put a plus right here, and then this would be a 2. So you could go through and see if you end up with something similar. I think you'll be kind of surprised that it's really, really close to this one right here. So let's take a look at the last one in this list. We've got an a squared, and then we've got minus 4x squared. So maybe a difference of squares right there, because that's a perfect square of a, and that's a perfect square of 2x. And then we've got an xy, and then a y squared. So you'll notice that these have a's and x's, and these have x's and y's. So the only thing that crosses over is just the x. We wouldn't have anything in common there. So we're going to use the technique that we did up above, except for we're not going to group the first 3 together. We're going to group the last 3 together. So I'm going to write this as a squared, and then you'll notice that every one of those is negative. Not really a fun thing to work with. So I'm going to do minus, and then this is going to be 4x squared plus 20xy. And then we've got, let's see, that would turn into a plus 25y squared. Now, we'll just leave this hanging off the end right here, that a squared, and let's take a look. This is a trinomial, and notice that it starts with a perfect square of 2x. It ends with a perfect square of 5y, and if you multiply those two together, you get 10xy, and if you double it, you have the right middle term. So this is going to be a squared minus, and this is going to be 2x and then 5y, perfect square. And remember, whatever the sign is in the middle, that's what goes right here. Now, you might look at this and go, oh, this is going to be easy. It's just like the other one because we've got a difference of squares just like we had up here. There's something that we have to be really careful of, and that's this. When we write down the two parts of this difference of squares formula, this is a perfect square of a, and this is a perfect square of 2x plus 5y. Those two things have to go together. So watch what happens here. If I write a and then minus 2x plus 5y, and I don't put that in parentheses, it's just a minus 2x, it's not minus 5y. So I need to put that in parentheses. And the next one is going to be the first one, which is a, plus the second one, which is 2x plus 5y. Now, when we're adding these, it doesn't make any difference. So I'm going to go ahead and write down a plus 2x and then plus 5y. But this one right here, it does make a difference. So I'm basically just distributing the negative through. So this needs to be an a minus a 2x minus 5y, and then we'd have that completely factored. Okay, so some great advanced techniques. If you know these, you'll be able to recognize and do more difficult factoring problems. But most of the time we just stick with the basics like we learned previously. The stuff in 3.5 is really just for practice and kind of showing you what might be coming up ahead, especially the two of these right here, difference of cubes and sum of cubes. So good luck on the assignment. Make sure you ask questions if you've got them.